Let's look at some examples of manipulating iterables and iterators. And let's just focus on using built-in functions and list comprehensions and dictionary comprehensions in order to perform some moderately complicated data manipulations. These are things that can be done in a line or two if you use the tools correctly. And manipulations like these often show up as the core part of some larger problem. So I'm just going to lay a bunch out there, and then I would recommend that you pause and just try them out on your own, and then we'll walk through them one by one together. So here's an example. What are the indices of all elements in a list S that have the smallest absolute value? So if I have a list S, the elements with the smallest absolute value are -2 and 2, but we want their indices. Indices in a list start at 0, 0, 1, 2, 3, 4, 5. So here are the smallest elements in absolute value, and their indices are 2 and 4. So how would we take this list as input and have this list be the output? Or if this list is the input, the smallest element by absolute value is the element at index 1. We're trying to list all of the indices corresponding to the smallest elements by absolute value, so we get a list containing 0. There's first exercise. I'm just going to go through them all. What's the largest sum of two adjacent elements in a list, assuming that the length of the list is greater than 1? So here's a list. If I sum these two elements, I get -5. That's not very big. Sum these two, I get 1. Well, if I sum these two, I get 6. So the answer here is 6 is the largest sum of two adjacent elements. Here's a similar list, but I've fiddled with the negative signs. And in this case, we don't get 6, we get -2 at the end. That's not what we want. We can get a positive number 1 by summing together 3 and -2. So that's the biggest thing we can get, adding together two adjacent elements in that list. All right, another one. Create a dictionary mapping each digit D to the list of elements in S that end with D, where D is an individual digit. So if I have this list of integers, I'm supposed to create a dictionary that says, here's all the elements ending in 1. Here's the elements ending in 3. Here's the elements ending in 4. Here's the elements ending in 5. Notice there are two of them, 5 and 55. There's only one for 8 and one for 9. And finally, does every element equal some other element in S? So given a list, is it the case that every element equals something else? Well, -4 only shows up once, so that's false. But here, 4 is there twice, and 3 is there twice, and 2 is there twice. So every element equals at least one other element. So this would give us true. So if you want to pause the video and work through some of these, I recommend that. Now we're going to go through and solve them. Okay, for the first one, what are the indices of the elements in list S that have the smallest absolute value? We're going to start with this example and try to work it out. So here's S. Smallest absolute value is not the min of S, but it's actually not the min of S using key equals abs either. That would give me the element in this that has the smallest absolute value. It wouldn't give me the smallest absolute value. So if my goal is to actually get the smallest absolute value, I would need to first call abs on each element and then take the min, which I can do by mapping abs over S. So now I have the min absolute value. What can I do with that? Well, I can find all the indices where the absolute value of the element at that index is equal to this min abs value, is equal to 2. This is different than finding all the elements with that absolute value, which I could do with a list comprehension. If I wanted to know all the elements, x, for x in S, if the absolute value of x is equal to min abs, that would give me both the 2 and the -2. But that's not my goal. My goal is to find the indices. And for that, I need to go through for I in not S, but a range of len S, which gives me all the index values for S. And we adjust this expression accordingly. We actually want just the index values. And we have to adjust this expression accordingly as well. We want to know if the absolute value of Si is equal to min abs. That will give me the numbers 2 and 4. So there's a two-line solution to this problem. Whenever I use a list comprehension, I could also use the map and filter built-in functions. So I could have rewritten this by first defining a filter function that takes in some index and tells me whether it's one of the indices that I want to keep. Then, if I take this same range of indices and I filter it using f, I almost get what I want, but this is a filter object. If what I really wanted was a list, then I would call list on it, and I'd get this same correct result. So I could have replaced this expression with this expression and gotten the same thing. Okay, let's go on to the next problem. What's the largest sum of two adjacent elements in a list S? And here we're using the same S that we had before. We're meant to get 6. There are two reasonable ways to do it. One is to think about indices. Range len S will give me all of the indices, but range len S minus 1 will give me almost all the indices. Here it is as a range. If I go through almost all the indices, just leaving out the last one, and I compute Si plus 1, then I'm summing together two adjacent elements for every pair of adjacent elements. And I'm leaving out the last one because there's no I plus 1 for the last element. So that's why I use this shortened range. Okay, this just gives me what all the sum of adjacent elements are. If I want to know the biggest one, then I should just call max on that. So there's another use of an aggregation function in order to do the work. Okay, so we're done with this. We can copy it in there and call it a day. Another way to solve the same problem, though, is with zip. So if I zip together S with S, I get a zip object. And what are the elements of this zip iterator? Well, let's list them out. They're giving me an element from S along with an element from S. These are not adjacent elements, they're just the same element. But if instead I had zipped all but the last element of S with all but the first element of S, now I have 5 elements here and 5 elements here. And when I zip them together, I see all the pairs of adjacent elements. So I had built two sequences, -4, -3, -2, 3, 2, and -3, -2, 3, 2, 4. Zipping them together gives me a list of pairs. What happens if instead of listing out the contents, I add together the elements in each pair? A plus B for A, B in zip. I get those same sums, of which the max is 6. So there's another way to solve the same problem. Okay, let's try another one. Map each digit D to the list of elements in S that end with D. The result is a dictionary, so we're going to use a dictionary comprehension. This one's going to get a little bit long, so I made some space. It's a dictionary where the key is a digit and the value is a list. The list contains all elements of S that end in that digit. So we look at X, figure out its last digit, and see if it's equal to D. That's a key value pair in the dictionary. We want one of these for every digit. For D in range 10 would give me all the digits. But notice in this result that there's no 2, because there's no element in here that ends in the digit 2. So I need to filter out some of the D's. We want to keep a D if any of the elements in S ends in D. We can use the built-in any function. Any of the elements in S ends in D is expressed as any element ends in D for all the elements in S. So this is the filter clause. Here's what we're iterating over, the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And for each digit that has this property, here's what we're building. Now, to figure out whether this actually works, we need to set S to be this value, and then evaluate our big expression. And look, that's what we get. So one implementation for this would be just to return that. And while we've solved this problem, this looks like a pretty long expression. So maybe we should be breaking it up in some way. One way to kind of break up this whole process into steps is to get the list of last digits in advance. So what are the last digits of all the numbers in S? Well, that would just be x% for x in S. Then we could rewrite this as, is this digit in last digits? And we get the same result. It's only a little bit shorter, but at least it only has one big gnarly expression instead of two. Okay, next question. Does every element equal some other element in S? And here's an example S. One way to solve this problem is to focus on some particular index. So let's say the index 1. Si is 3. There it is. We could figure out if 3 appears anywhere else by building a list containing everything except for this. S up to I gives me everything through 4, but not including the 3. Si plus 1 on gives me everything after the 3. So if I were to add those together, I'd end up with everything in the list except for that 3. We haven't gotten rid of all the 3's, we've just gotten rid of the element at index I. And I could ask whether Si is in this new list that doesn't have element I in it, and it is. That means that 3 appears somewhere else. So now that we have an expression to check whether the element at index I appears anywhere else within the list, we could just check that for all the i's. Is it the case that all of the following are true? This expression, Si, is in the rest of S, not including I, for every I in rangelen S. Let me just write that all on one line correctly without forgetting the last parenthesis so you can see what's going on. So that's one way to solve this problem. But there are other ways to reason about the same thing. Like, let's say we didn't want to do it about indices. We just wanted to look at the values themselves. Well, one useful expression would be y for y in S if y equals 3. Tells me how many 3's there are. I could get how many 3's there are by taking the length of this. Or as an alternative, I could collect 1's instead of 3's and get the sum in order to figure out how many 3's there are that way. But we don't care about how many 3's there are. We care about how many there are of any particular value. So we could write this same expression as part of a list comprehension. I think this one might get long. Where instead of the 3, we want every x for x in S. What do these 2's mean? This means that there were 2 4's, that there were 2 3's, that there were 2 2's. And then this is kind of redundant. There are 2 3's, there are 2 2's, there are 2 4's. If we want to make sure that each of these is above 2, then one way is to say that these are all greater than 1. Another way would be to compute them all, find the minimum value in there, and make sure that that minimum value is greater than 1. Now you know that they're all greater than 1. So just 2 ways of writing the kind of equivalent idea. And all we're doing here is just counting the number of times that x appears in S. And in fact, it turns out that that's built in. I could just say s.count how many 3's there are, and it will tell me. So I could simplify this a bit by saying I want to know s.count x for every x in S. And it will tell me that the smallest count there is 2, and since those are all greater than 1, we know that every element equals some other element in S. So maybe that's the simplest way to solve this one. Okay, and if we did this right, then all of our doc tests should pass, and they do, so it appears that we've solved all 4 of these problems.